This is the Advanced Functions lesson on 3.6, Factoring Polynomials. Let's review some of the factoring methods that we already know. We already know that the greatest common factor is what you always look for first, no matter what kind of polynomial expression you have. A binomial means there's two terms, and if it doesn't have a greatest common factor, you can check to see if it's a difference of squares, factors like this if it is. A trinomial is three terms. It's not a degree of three. So sometimes your trinomial, your leading coefficient's a 1, sometimes it's not a 1. We have different methods for that, sum and product or crisscross or decomposition for factoring trinomials. Then everything after that, quadnomial is really 4 terms. We don't use that phrase very often, but sometimes we can do factor by grouping, and there's an example in your textbook of that. But often once we get to something higher than a degree of 3, we need to go to long division. So it doesn't matter if it's a binomial or a trinomial, the degree is 3 or higher. If it's not a quadratic, then we have to use long division. So we've got some theorems today. We're going to talk about the Remainder Theorem and the Factor Theorem. So I'm just showing them to you here, but they're going to come up again in our lesson. Here's a little aside, a little piece of information that isn't terribly important, but I wanted to put it into. When you have an expression like this is a trinomial, it has factors, and these are its factors. And these factors have zeros. So here are the zeros of that equation. If I took those zeros and put them into brackets, it would look like this. So this equation has the same zeros as this one. But if we expanded the one with the fractions, it would look like this. And that's not the same graph as this one, right? We're off by a factor of 6. So most questions today are not y equals because we're only looking for factors and roots. We're not graphing. If we were graphing this has an a value of 6. This one does not. So they'd be in the same family of functions, but that's just why a lot of times you don't see the question starting with the y equals. Example 1. Given this cubic function, determine if each binomial is a factor of f at x without dividing, and if not, determine the remainder. So here we're going to talk about the factor theorem. This, x minus 1, this little binomial, I want to know if that divides evenly into this expression, and I'm not going to use long division for it. I have a very handy little theorem called the factor theorem, and it says that x minus a, so x minus 1, is a factor of f at x if and only if f at a equals 0. So if that is the case, then it's a factor. So that means f at 1, right, it's the opposite sign. When I sub in an f at 1, if I get a 0 here, then this is a factor. I didn't even have to do any division to figure out if this would factor evenly. So the factor theorem is a special case of the remainder theorem. If I sub in a 1 into here and I get a 0, that means the remainder would be 0. It means it divides in evenly. It's like doing 16 divided by 4 as opposed to 16 divided by 5. So let's sub in f at 1 and see what we get. So we're just going to do the math here, subbing it into the equation. Always substitute using brackets, and that's mainly so that when we have negative signs and exponents, we make sure everything is in order. 1 squared minus 10 times 1 minus 8. That gives us 1 minus 1 minus 10 minus 8. What is that equal to? So 1 minus 1 is 0, right? It's minus 18. So that is not a factor. And the factor theorem says that if we got this to equal 0, if it were equal to 0, then that would mean x minus 1 divides evenly. It's a factor, but this didn't happen. So therefore, this x minus 1 is not a factor. So a factor has to divide in evenly with no remainder. This one's not a factor. So let's look at the theorem again over here. The factor theorem, x minus a is a factor if and only if, when we sub in the opposite value here, we get 0. We didn't get 0, so it's not a factor. But what we do have is a point on the graph. If I had to graph this, I would have a coordinate 1, -18. So it's just a point on the graph, but it's not an x-intercept. It's not a 0. It's not a root. So this one didn't work. Let's try the next one. F at -2. So I'm subbing in, I'm taking the negative. This is the potential factor here. So I'm putting in whatever value for x. What would I sub in for x to make this whole piece equal 0? And that would be when x is -2. So I'm subbing in -2. That is, so I'm going to press pause and I'll fill it all in, and you press pause and do this one yourself. So we got a 0 here. That means what we have here is therefore x plus 2 is a factor. And what we have here, so if we were graphing this, -2, 0 would be a point on the graph. Over here we would have 1, -18. So what we're looking for are those zeros, those roots, those intercepts. Those are where our factors are. Erase this. So in the box I have, if our leading coefficient is 1, or in this case, since our leading coefficient, this is a 1 here. Since our leading coefficient is 1, we can look at the numbers that are the factors of the constant. Here's my constant here. So the only numbers that will work in this case are numbers that are factors of -8, and these are what they all are: 1, 2, 3, 4, 8, -1, -2, -3, sorry, no -3, -4, and -8. All of these numbers are factors of -8. They divide evenly into our constant term. Any of those divide evenly into it. So we're going to check those, all of those, to see which ones are factors. So we're just testing at the factor theorem. Normally we wouldn't go through all of them, but because we're learning the factor theorem right now, we're going to check out each one. So we already did f at 1. That's right here. F at 1 is -18. We've already done that one. We also have to figure out f at -1. So we have to get the positive and the negative of each factor of 8. Even if that weren't a -8, even if it were a +8, we still need to do positive and negative factors. So all of these we're going to go through. We already did f at -2. Up here, we already got that one to be 0. We have to see if f at 4 will work, -4, 8, and f at -8. So I want you to, well, you can press pause here and calculate them all. I'm going to write the answers in for you. So the other values, we have f at -1, you sub that in, and hopefully you got a 0 there. F at 2 is a -24. Remember, this is still a coordinate on the graph. If we were graphing it, these are all valuable numbers. If you're just doing it on your calculator and you're not writing it down, it's worth it just to write down the answer, because if you have to graph it later, you've got all these points ready to go. F at 4, you sub that in, and you saw that was 0. So that's another factor. F at -4 is -48. F at 8 is 360. I probably wouldn't be graphing that one. And f at -8 is -504. So I wouldn't be graphing that one either. So the question told us to factor completely using the factor theorem. So here are our factors. Let me kind of highlight them here. So I have, this is a factor. This is using the factor theorem, this gives me a 0. I'll write out the factors in a second here. So these are our 3 values that worked, which means from that, so let's look at our first one. I'm going to do the first value we found here. If f at -1 is 0, then that means, we already talked about this, that means x minus 1 is a factor. This use of the factor theorem tells us that x plus 2 is a factor, and our third one is x minus 4. So these are all equal to f at x, our original function. Using the factor theorem, we found all of the factors of the function. So sometimes we get numbers we get many, we would have to go through many numbers to sub them all in. We're not going to do that today. I'm going to, just for this example, I wanted you to sub in all of them just to try to get an idea of what the factor theorem is. So that's the factor theorem. The factor theorem, you sub in a number and you get 0, then that means it's a factor. It's one of these. If 2x plus 1 is a factor of this, and 2x plus 1 is going to give us a rational root, x equals 1/2, negative 1/2. In our previous example, we didn't have, we had nice, easy linear factors, x plus 2, x plus 1, x minus 4. We didn't have a coefficient in front of the x value here. So how do we get these ones? Another way of writing this is to say that x plus 1/2 is a factor, which is the form we're going to need if we use synthetic division. So normally we would not do what we did in the previous example, which is to go through all of the factors, sub them all in. Once you have one factor, then you can use division, and we've already practiced this. So we're kind of going back a few lessons here. So you've got one factor, and then you divide to find the rest of them. Example 2, determine all other factors for the above, that's this one, polynomial using division. So we're given one factor. There's my synthetic. I know you guys love synthetic division. I would not. I would use long division for this question for sure. But since I know many of you choose synthetic division, I'm going to go over it with you because this one has a fraction. So I would be doing long division here, but I know a lot of you like this, so let's do it this way. I put in my coefficients, 2, -3, -8, -3, all down here. And then we do the division, synthetic division. So the first step is to bring down the first coefficient, that's a 2. Then I multiply the negative 1/2 times 2. Negative 1/2 times 2 goes up here, that's a 1, negative 1. Add -3 and -1, we get -4. -4 times negative 1/2 is going to be a positive 2. -8 plus 2 is -6. -6 times -1/2 is 3. And what a surprise, we get 0. This is a remainder, right? This is 0. And it's supposed to be 0 because the question said it is a factor. If you see the words that something is a factor, you have to get a 0 remainder. If it's a factor, that means on the graph, it's hitting the x-axis. No remainder, you should have no y value there. So if we didn't get 0, I would erase this and start over again because its question tells me it's a factor. It has to work out like that. So determine all, the question A says determine all other factors using division. What I've got here so far is my original question was 2x cubed minus 3x squared minus 8x minus 3. So I now know that's equal to the factor of, well, they gave us 2x plus 1, but we changed it to x. We actually used the 1/2, right? So that's what we have to put here, x plus 1/2. And what I was left with, so this is my x squared term, this is my single x term, and this is my constant. 2x squared minus 4x minus 6. We can factor that. First of all, remember the first thing you always look for is your greatest common factor. This trinomial has a greatest common factor of 2. So let's take that 2 out. So I'll put it in between the two brackets here, x plus 1/2. Then I pull out a 2, and my trinomial is now x squared minus 2x minus 3. So distributing that 2 back in here, I have 2x plus 1, which was the original factor in the very top line of the question. 2x plus 1, and this trinomial can be factored into x minus 3. So this is just a sum and product question here. X minus 3, x plus 1. So I've figured out all of the factors without having to sub in a whole bunch of numbers. The question said determine all other factors, so these are all of the factors here. Those are all the factors. It's completely factored, and we used division for that. Now, because we used synthetic division, we had this little kind of weird issue happening here with these fractions and having to change it. That won't happen if you use long division. If you use long division, you would just put your, I'll put up at the top here, you would just write your 2x plus 1, and then your long division, and then your polynomial expression would go in here. I'm not going to do it all again, but you would do your long division and you wouldn't have to worry about these fractions. Part B, how would you determine that a equals negative 1/2 is a 0 on your own? So how would we get this on our own? Because the question told us this factor, and it turned out to be a 1/2. How would I get a 1/2 on your own? So this is still part of our factor theorem. It's just more complex here. What we do is we take let the leading coefficient that you have in your polynomial, in this case we had a 2. This is my leading coefficient. Let the leading coefficient be represented with a q. And we're going to think of all the factors of q. So all the factors of 2 are 1, 2, -1, and -2. So that's our first step. We get all of the factors of the 2. Then we're going to use p. I didn't pick these letters. We're going to use p to represent the constant term. In the previous example, it was an 8, remember? And we got all the factors of the 8, 1, 2, 4, 8. So in this case, we've got a 3, so we've got a positive and -1, and we've got a positive and -3. So we have to look at all the factors of the leading coefficient, and we have to look at all the factors of the constant. And what we do with those, we put them together, and we take all the p possibilities, put them over all the q possibilities. You have to get every possibility right here, and we're going to list them all. So all combinations, plus or minus, of all of these terms. So let's start with this piece here. So we have to do p over q. So let's start with the 1. So our possible combinations of p plus or minus p over q, just so I don't write everything out twice, I'm going to do them together. So we've got plus or minus 1 over, and now I go up here. I'll take the first one, 1 over 1. That's one possibility. We could also do 1 over, let's go to the second one up here, 1 over 2, plus or minus. Now I don't have to keep going with this 1 and with this 2 because I've already done the plus or minus. So I don't have to keep listing them all. I've already got those combinations. So far I've got one of the factors is a 1, the other one is 1/2, plus or minus. Now let's look at the 3. There's the 3, so we're going to put the 3 on for the numerator. Now the 3 needs to go over all of these. So we can have 3 over 1, and we can have 3 over 2. So I'm going to just clean that up a bit. All of our possible combinations are a plus or minus 1, plus or minus 1/2, a plus or minus 3, and a plus or minus 3 over 2. These are all possible factors, but as it turns out from the question, when we take a look at the solution, we already figured it out here. We were given this one. We were given this one already, right? That's one of them. The others were x minus 3. That's from here. There's your plus 3. And x plus 1. That's from here. So all of the factors come from these possibilities. That's how you would figure this one out on your own. The previous example, we subbed in plus 1, minus 1, plus 2, negative. I didn't do any fractions yet. We just took nice integers. But certainly fractions are a possibility. Example 3. We have a polynomial, but we've got an a and a b in it. So we've got some clues here in the question to help us find what a plus b is. This is the remainder theorem we're talking about. The remainder theorem, it's just like the factor theorem. When you have a polynomial and it's divided by x minus a, so say divided by x minus 1, the remainder, in this case 1, is equal to f at a. So what that means is, let me get the, first of all, I'm going to put a f at x in here. The question didn't have an f at x, but we're going to start with this just so that we can, it's easier to substitute in f as 1, f as 2, right, when we have this notation. So I'm going to start with that. So f at 1, we're going to look at this clue right here. When it's divided by x minus 1, that means I'm subbing in a 1 from here, subbing in a 1 into all of these x's, subbing in a 1. And just tidying that up a bit, we have f at 1 equals a minus b plus 1. But we also know that f at 1, the question said when f at x is divided by x minus 1, the remainder is 1. So f at 1 equals 1. If the remainder is 1, then I know that when I sub this f at 1 in, I should be getting a 1. So let's replace the left f at 1 with a 1 here. This all has to equal 1. So this is the remainder theorem. When we divide by x minus a, the remainder is equal to when we sub in. So I just brought the ones over together and they make a 0. So I have 0 equals a minus b. Now that's no good. We've got 2 unknowns and 1 equation. We can't solve that. So luckily, there's more information in the question that we haven't used yet. When this polynomial is divided by x minus 2, the remainder is 36. Okay, let's put that piece of information in. So I take 2 from here, because if I subbed a 2 in for x, I would get a 0. So I put a 2 here, 2 in for all of the x's, clean it up, and remember that. So there's all our constants collected there. Remember the question said the remainder is 36. So if the remainder is 36, therefore f at 2 is equal to 36. So I take this f at 2 and I put a 36 there. And I'm going to collect my numbers, bring the 8 over. And again, I've got an a and a b. 2 unknowns again. So we're going to put both equations together. Well, first, I'm going to take this equation right here. I'll write that 0 equals a minus b. And now I have this one. Put it underneath. 28 equals 8a minus b. So here I'm going to do substitution or elimination, going back to grade 10, equation 1, equation 2. Pick the method that you like the best. Well, the easiest method. Well, let's do elimination here. So elimination, I'm going to, these b's already match, so I'm going to subtract. 0 minus 28 is negative 28. A minus 8a is negative 7a. And the reason I chose elimination here is because these are now gone. Negative b subtracting. You don't have to use this method. You could use substitution because these terms are already pretty much isolated. So it's pretty easy to take a or b and just sub it directly over into this one. Anyway, divide by negative 7, and we get 4 is our value for a. Remember the original question, look up to the top here. The original question said find a plus b. So I now know a is 8. I have to find b. To find b, you can sub into either one of the equations, whatever one you like better. Probably the easiest one is we're going to sub into the first one we got, which is 0 equals a minus b. 0 equals our a is a 4. Bring the b over. B equals 4. So they happen to equal the same thing. A is 4, B is 4, therefore the question actually said what's A plus B? A plus B equals 4 plus 4, 8. Example 4 is our last one. List all possible zeros for this polynomial, then identify the ones that are zeros. So 0 can be written. A little English lesson there for you. You can write 0 both ways. Okay, the first thing we're going to do is remind ourselves of the factor theorem. The factor theorem is the one we're looking for here. We're going to find all possible zeros, and then we're going to find the ones that actually are. So we're going to list, using the factor theorem, we're looking for the ones that equal 0. So first we have to find all possible P over Q combinations. P over Q, remember what P over Q is? It's the constant. P is the constant. And Q is the leading coefficient. So let's start with our constant. This is P up here above the equation. Over the 1 I'm putting a P, and over the 4 I'm putting a Q. So P over Q, I'm going to start with 1. So that's nice that I have a 1 here, because I only have to worry about 1s for my numerator. So my possible combinations for plus or minus P over Q are all going to have a 1 in the numerator. So I'm going to have a plus or minus 1 over. Now, all factors of 4, let's start with 1. That's one possibility. Then I have 1 over my next factor of 4 is a 2. And I have 1 over 4. Those are all of my possible combinations, possible zeros. And I'm just going to erase the first one and just turn it into a 1, because that's a little easier to look at. So plus or minus 1. 1, 1/2, 1/4. We have to sub all of those in. So it makes it a little easier to sub it in if I call it f of x instead of leaving it as a polynomial expression. I change it into an equation just for substitution purposes there. So I've got to sub in my 1s and my negative 1s. Those are these two right here. Then I have the 1/2s to sub in, and I have the 1/4s to sub in. So we're going to sub in all of those and see what we get. Now, normally what is usually easiest to do is to just go until you find 1. You find 1 that works, then you go to your division and figure out the rest. We don't have a whole lot here, so we can sub them all in just for practice with our factor theorem. It didn't tell us in the question that we had to use the factor theorem to find them. It just says identify the ones that are zeros. So I could have gone and done my division. I'm just going to practice again with the factor theorem, but remember, you only need to do this until you find 1 that equals 0. As soon as you get one of these to equal 0, then you can go to your division and finish your question the way we've done in the past. But we'll go ahead and we'll try to sub in a few. So I want you to press pause here and do these calculations, and when you're done, press play. So here's what I've got. As soon as I got 3 zeros, I stopped. I don't need to figure out these ones because my question is a cubic. Right here, I covered over it, but that's a cubic there. There's only the maximum number of zeros you can have is 3. So I don't need to keep going any further. I've already got 3 zeros. So this, change colors here. The first one tells me that my factor would be x minus 1. This one tells me that my factor would be, so let's be careful here, x minus a half, but we don't write it, we can't write it with fractions, so I've got to rearrange that. Remember how to write that properly is really, so let me put over here, if we've got x minus 1/2 equals 0, I bring the 1/2 over, x equals 1/2, I multiply both sides by 2, 2x equals 1. Now I can bring the 1 back over again, 2x minus 1 equals 0. So there's my factor. So the factor that I'm going to write here is 2x minus 1. And then this one yields a factor of, we do the same thing that we did before, and we write it as a linear root of 2x plus 1. And the question said identify the ones that are zeros, so we've identified the ones that are zeros. I could also rewrite the question I had. My original question was 4x cubed minus 4x squared minus x plus 1. That's equivalent to writing x minus 1 times 2x minus 1 times 2x plus 1. So the zeros are at x equals 1, x equals 1/2, and x equals -1/2. Be sure to use the examples in your textbook for further illustrations of this concept. So almost every question in the textbook has a matching example to go with it, or else I have a matching example right here. So every question that you do in your textbook, look through the video to help you, because there will be a question just like it here, or there will be one printed in your textbook already. That's the end.